So, talked last week about wanting to start each class with a review of the questions before. In order for us to be able to really do that, everybody has to be able to get them in before class. I may, in the future, change my mind about that, and it's going to benefit you guys to review the questions anyway. And those of you who don't have them done before class might just not get an opportunity to have them in. So, unfortunately, we're going to continue the way we're going right now. With maybe next week, we're going to be able to get everybody's review questions in before the beginning of class so we can go over them. That is a benefit to you guys. But we can go from there. Pretty much everybody, just a few outliers that need to participate a little bit more. But let's see. I think that's all I wanted to really say about our homework stuff. For those of you that got an opportunity to get it in a little bit after it was required, I did take 15% off the top. I feel like that's fair. I couldn't really give you 100%. Okay. Interrupting class. Okay, so holy guacamole. We're recording this too, Scott. All right. From the beginning. Magnetism review. Just so we get caught back up with everybody and everybody's on the same page. Let's talk magnetism review. I'm not going to spend a lot of time on this unless we have questions. So we're just going to hand it to you. We're going to have north and south magnetic poles, like magnetic poles that help on line track. Types of magnetic material, paramagnetic, paramagnetic, diamagnetic, pole Ferris, you get the lights down a little bit. Somebody read that next one. Current flowing through a wire creates magnetic fields. Everybody pretty happy with that? The direction of current flow through the wire determines the polarity of the magnetic field. Electromagnetic strength is determined by the ampere turns. And the core material affects the electromagnetic strength. Let me ask you guys this. Do you think that this or this would have a stronger magnetic field? I think so too. We don't have as much material to deal with there. We can test that too someday. Maybe today, this afternoon, if we get crazy. Okay, we're going to just touch, this is just a short little deal here to kind of clear up anybody's feelings about, there's a good graphic on here about magnetic induction. Just a short little.
The purpose of an inductor is to oppose any change in the magnitude of current within a circuit. The electrical property that resists either an increase or decrease in current is known as inductance.
That's what we talked about on what, Friday?
Is created when an electrical current flows in a wire wrapped around a magnetic core. You may recognize this as an electromagnet represented by flux lines that develop around the core with the formation of a north and south pole at their respective ends.
What would have happened right there when we opened that up and that collapse of that magnetic field? Let me pause it real quick.
Or light bulb to this circuit.
Remember what we talked about late last week about whenever we open this switch up, what happens? Boom! Right there, voltage spike because of the collapsing magnetic field and the instantaneous removal of the current through the system. And then what we would have in here, between here, would be something like a Travis. What would we put in here to eliminate voltage spike? Possibly. Diode, MOV. Yep, good stuff. Okay.
As the switch is closed and the current flows through the circuit, the electromagnetic field in the inductor forms and expands rapidly. However, because of the unique properties of an inductor, as the flux lines of the electromagnetic field expands, the changing current generates a voltage that resists the current coming from the source. The maximum
Who remembers what that's called?
Flow occurs at the instant the switch is closed.
What is that opposition to the applied voltage called? Induced voltage, very good.
Therefore, the bulb will not turn on instantaneously.
Remember that was the time constant stuff we were talking about?
It stops expanding based on the level of changing current. The flux will no longer generate an opposing voltage in the circuit.
This is magnetic saturation right there.
And reach its maximum value at the defined time constants for 5t, where t is equal to L divided by R. The light bulb will then be at its maximum brightness.
Time constants were 63 and 2/10 apart, going up that line.
The electromagnetic field will diminish rapidly and simultaneously release stored energy in the form of voltage. It will actually generate enough voltage to cause a spark across the switch as it opens. Whereas a capacitor uses voltage to store energy, the inductor uses current. The inductance.
Yeah, okay, that's pretty much the long and short about that. Know about that right there. So everybody's pretty clear on that. There's a nice little graphic there to actually explain what the book's trying to tell us. So let's get out of this. So when current flows through a conductor, a magnetic field is created. We all remember that. When magnetic field cuts through a conductor, a voltage is induced. We talked about that a little bit the other day, and lab guys got to see us induce voltage just by moving this magnet across this magnet right here. Very small voltage, but this did happen. You'll see it this afternoon, my other guys. So the polarity of the induced voltage is determined by the polarity of the field relative to motion. Induced voltage can be determined by the turns of wire, field strength, and the speed of cutting action. So everybody's faster you move this across the top of here, say this goes on electromagnet, the faster we move this across here, obviously the more intense we're going to have our results. We'll start to really see that come into effect as we start to break into what we're going to talk about Friday is DC generators, or Monday probably. So induced voltage polarity always opposes the applied voltage, which we can clearly see here on our deal that we're going to end up talking about today, our waveforms. So this is the induced voltage, our applied voltage, and this is the induced voltage and how they're opposing each other, going through the AC wave. Inductors oppose the change of current. We saw that in the graphic there with how we weren't turning the light on right away until the magnetism got completely overtaken. Current rises in an inductor at an exponential rate. Remember the curve there, the big curve that we had starting from model 0 and going up at 63.2% per time constant to where it got to almost 100%. Hopefully everybody remembers that. And finally, inductors can produce an extremely high voltage when the current is removed. I think we already talked about that. So let's move forward. Now that we're reviewed, let's start talking about something that we haven't. So inductance and AC circuits. Now we get to see some actual pretty cool stuff happen too. So right here, what we have in this picture is we have a voltage meter that is going to be this circuit right here. We have an ammeter, which is going to be down here in series with our inductor, and then we have the actual inductor. What we're wanting to find out and prove out here is we want to know what the actual current drop is across this inductor, because we're not. There's going to be a current drop across here. This is somewhat acting like a resistor, but it's not. It has current properties, especially in DC situation like that here. What we want to do is just figure out what's going on here. These are the items that we're presented with here. Using our own law, we can obviously tell here we have the 3 pieces of the puzzle that we need. So if we were to calculate this out, in my question here, what is the amps? What is it? Whatever, you need to know right there. You guys shouldn't even have to think about it. Look at it. Okay, one. So right there, right? All right. Okay, so that one we got, it's just a purely almost identical to a resistive load. Apart from it being an inductor, it could essentially be a resistor as far as our Ohm's law is considered. But that really doesn't apply when we move from DC voltage into AC voltage, and we will talk about that right now. So inductance, we all remember that. That's the little definition up there is for your benefit. In some instances, some inductance is present in all alternating current circuits because of this, right? The fluctuation from positive to negative in the AC sine wave, because it's continually changing its magnetic field. But it's not generally considered in a circuit calculation unless the circuit contains a coil, which we are going to be talking a lot about because every motor is a series of coils. So that's why we have to know about this stuff. In AC circuits, the magnetic field continually changes magnitude and direction and induces voltage 180 degrees out of phase and is always opposed to the applied voltage. So that's what I have going on up here. So this is our applied voltage. It doesn't matter what it is, what the peak to peak is right here, or even what's RMS stand for. What is that? Root mean squared, right? What is that, like 73% of the peak to peak, I believe? Divided by 0.707. Yeah, maybe that's 20%. Yeah, he's right. So if I say 73, that might be because so yeah, but we do know that there's a difference between peak to peak and root mean squared, and if we really need to, we can find a formula and figure it out. But for this, we don't need to. So what I'm trying to say with this is that in this AC wave, the induced voltage is going to be, when it's on the positive side of our graph here, it's going to be 180 degrees out of phase. It's going to be, so this right here is the opposing wave of this induced voltage. So what we think of here is that as this voltage is being applied up this way, the opposite is going to be coming back this way. So pretend our inductor is out here in this sine wave. The applied voltage is trying to push this way, and the induced voltage is pushing back. That's basically what they're trying to tell you right there. Okay. So here we go. This is the same setup, except for now, we've changed our voltage from DC to AC, and now look what we got. The exact same voltage as before, the same inductor as before, but what in the world is going on with our amps here? It's dropped significantly, right? And it's all because of the properties of an inductor in an AC circuit. So that's their actual graphic for it. And here's their explanation of the applied voltage. This is, how many cycles is this right here? One cycle. So it starts here, up, down, and back up. So one cycle is showing us the difference there. So let's see. Computing the induced voltage. The amount of induced voltage can be computed if the resistance of the wire and coil and the amount of circuit current are known. So we got our old friend Ohm here. And he's going to tell us that, well, we automatically know what in the circuit that we looked at when we grabbed this. Well, let's pretend that we. So right here, and what we have going on here, in our 53 volt AC system circuit with a 60 hertz rating, we know that here from our measurement that our amperage drop across this inductor right there is 0.4. So if we're using that, we can figure out the rest of the equation, which we eventually will. I don't know if we're there yet. That's pretty simple stuff there. Anybody have a problem with figuring out what the induced voltage is? Everybody gets that? Induced voltage right there at the beginning part of the chapter. The example they used, I think, was 4.8 volts on the end. It's not too terribly difficult stuff there. So in the case they used in the book, they took their meter out and they used their amp meter, and they figured out that they drew 0.8 amps. Let's see, what was their voltage? 120 volts. We can draw that out real quick just so everybody's on the same page. I'm going to have to get rid of Scott's transformer. Man, he's got some beautiful handwriting. Almost ashamed to erase that stuff. So in our 120 volt circuit, 1, 2, 0, B, A, C, and we got, what's our resistance? 6. So that's our V. Now we got 6 ohm. And using those two, we should be able to figure it out, right? Or what else? We're looking for induced voltage. That's what we're looking for. So on this particular example, this gentleman or lady has determined using a clamp meter that the current draw across that inductor and the resistance of the circuit is 6 ohms. With the ohm meter, and the amperage drop is, what is it, 0.8? So what it's trying to tell us here is that to figure out the induced voltage, we're going to take the current, which is 0.8, times the resistance, which is 6, and it's going to give us our 4.8 for voltage drop across that inductor. That's all. I mean, you guys have done that 1,000 times with Scott when we're talking about resistive loads. This is pretty much the same thing. Instead of a resistive load, it's an inductive load. So, I mean, the theories and the principles that are behind this are very similar to resistance. So let's see. Inductive reactance, induced voltage can limit current flow through the circuit in a way similar to resistance. So that's basically what we're talking about here. Instead of using a resistor here to do what we got over here, which we easily could, but that's not what we're talking about. We're talking about inductors. So in resistance, the resistance to current flow or voltage flow in a DC circuit is just called resistance. But when we're talking about inductance in AC, and especially talking about inductors, our measurement is going to be called inductive reactance, or just in this case reactance. The symbol is the letter X, and it's measured in ohms. Reactance caused by induction is inductive reactance, and here's our sweet little formula down here. We ain't going to spend too much time with that until we get a little further. Actually, we could probably go back to that. I think that might even be actually the one that I want to talk about over there. So who thinks they can figure that out over there if we didn't already know what the value was there? I think I wrote some stuff down, but I don't know if it's right. We can check it out though. So what I'm looking for is I plug this into example 2 on page 45 in the book. That's the current drop from the circuit. Yes. So if we apply what we first want to do is figure out what XL is, sort of go along with this guy right here. We have all the information to draw that.
what I really want to solve for is what the inductances in the circuit. So that's how it's going to be running these. So let's see. What do you think? What do you think about this? I got the notes right over here.
Everybody see that okay?
Yeah, we do. So we're going to first figure out what our X now is. So we have both two currents going through this thing. 53 volts AC, and a current of 0.4 amps. We'll come up with 4 XL. So this equals XL. How much? Everybody agree? 50. Oops. Yeah, say 56. I meant to say 53. My fault. My fault. I didn't agree. It should be 53. My apologies. So our XL in this case is XL equals 33.5. Very simple stuff right there. But let's actually figure out what the energies are on this guy. So then we have that secret formula there that might square the stuff. L equals the total inductance in our circuit divided by 2 pi f. So what's 2 pi f? What's the magnitude, first of all? What's pi? A delicious dessert. Yes. 3.14. I remember high school algebra class that makes you remember now. 3.1415 ounces. Yeah. And I think the next one was 6.2. 1.62. Yeah, that's just what do I do? That's what I got. Everybody happy with that? Okay. Okay. So, moving forward.
We may calculate some more of this stuff, but in a big picture of the motor world,
when you're out there putting your hands on the amount of inductance that you're actually going to be calculating is going to be very slim.
unless you get into a motor rebuild shop, which is possible, and then you'll definitely be spending a lot more time with this. But at that point, you will have the basis to be able to expand your knowledge from the folks that are working there with you and come up with a little bit more solid foundation as far as what you need to know for that particular job. But we're just trying to give you the a little tiny picture of what is actually going on inside of that bugger. So, but can I count the number of times that I've actually had to calculate what the actual inductance is in the circuit since I've left school? This will be 1. So keep that in mind. Good information to kind of have back there, but not a lot of use for us in the real world. So here we go, talking about some more coils. Everybody pretty solid with the fact that if you add more coils, you're going to get more inductance, and if you take them away, you're going to get less. Pretty solid with that. So we know, obviously, by looking at that first picture, the amount, I mean, it was a fairly small coil that we had that first inductor with a 53-ohm program here. Fairly small, wasn't incredibly huge, but they were using a very thin wire. And you could imagine to get that thickness, they probably wrapped that bugger quite a few times. So get quite a little bit of inductance with that guy. So here we go again. So this will be kind of the final little part of this.
And this is even illustrating further about magnetic inductance in, or excuse me, what are we talking about?
Not magnetic inductance, inductive reactance. All those words sound the same to me sometimes.
But here's kind of the end picture of what we're going to see with our electromagnet, and why this is such a kind of cool feature that this kind of stuff has, is we've almost completely eliminated the amperage in the circuit. Almost completely. All we did was we turned that inductor into what? What do we do here? We have a coil, and we threw some steel in it. We created an electron right there. And now we've taken, here we have the iron core to the inductor, creating an electron. This also demonstrates inductive reactance. See how low the current drops. So we dropped that sucker down almost zero just by throwing that inductor around the 94. How large of a resistor would we need to do the same effect? Who knows that? How much? Pretty close. 33 parts, right?
Did you calculate it?
Oh.
Yeah. Yep. I know what it is. Who else knows what it is?
833. Yep.
Yeah, so 833 ohm resistor we just cleaned out with this little system right here, and having the other properties. So pretty neat little deal. So this is what we were looking at a little earlier with this program over here. Current circuit is limited by inductive reactance. What it's trying to tell you? I think what we talked about says here in my note. Let's talk about example 1 on page 44. We already talked about example 2, so that's probably not really necessary. You guys feeling pretty confident about that? Everybody okay? Phil, you all right? All right, looks like it. Okay. Reed, are you singing in lullabies back there or what? Yeah, okay. All right, schematic symbols. Inductors represented by a coil of wire. So in my very best over here to illustrate the two difference, there would be the long pump one, and then here's the little squiggly stuff. And then as you can tell, that in both of those examples before we added the iron core, what we have here isn't what we have here, right? We threw the iron core in there. On my last example, that would have to be a symbol that would be drawn in there. So, not really much else to add to that. So connecting inductors. Inductors connect in series. Total inductance of the circuit equals the sum of the inductances of all the inductors. Total inductive reactance equals the sum of inductive reactances of inductors. And seashells by the seashell. No, it's about the inductive reactance. And so inductors in parallel is going to be what you guys suppose. Pretty much the same thing as resistors in parallel. The reciprocal of total inductance equals the sum of the reciprocals of all inductors. Everybody remember that formula? I hope so. I hope you do. And then my little note, geez, doesn't this sound kind of familiar? Yes, it does, because it's pretty much the same thing here as it is in actual resistive circuits. Okay. Any questions there? Everybody remember the formula? Okay. So voltage and current in a purely resistive circuit. Current and voltage are in phase with each other. This is the example of what we've got going on here. Here we know, since this is a resistor and not an inductor, there's going to be no increased voltage because there's not an inductor. So these things are not having any outside influence added to them and just flowing along smoothly like they are.
Voltage and current relationships in an inductive circuit. And here we inductive circuit, current lags voltage by 90 degrees because the induced voltage is proportional to the rate of current change. So this is why I got these lines up here, is because I want you guys to understand is that where in this wave do we think the least amount of current change is going to happen? So maximum voltage occurs when the rate of change is greatest. The rate of change decreases as current reaches its peak. So voltage decreases as follows. Maybe that's not what I want to say. Okay. Trying to fill this in, what I'm talking about is where this stops changing the most. Here, we can see as this wave starts to begin, we have a constant rate of change all the way up until we reach the pinnacle, peak of our wave. And from that point on, we're not changing. It's not going to go any higher. So maximum voltage occurs when the rate of change is greatest. So at this point right here, our rate of change is the maximum for this wave. So at this point, guess what happens? Current starts happening because of the new system. And so to follow that through, since these are inversely proportional, when this guy starts at its maximum rate, this guy starts climbing up here. Our current wave starts climbing. And then when this is at its minimum, our voltage is at its minimum, look at what we're at here. Our current is at its maximum. Because of the induced voltage lags current by 90 degrees, and it is 180 degrees out of phase with the applied voltage, current lags the applied voltage by 90 degrees. So you can tell right here how I got this drawn in here, that when our peak is matched to our peak here, if we were to have this degreed out in an actual grid, we would be able to kind of see the 90-degree difference between here and here. Let's see if I can probably another way to describe that. So if this was to be in a circle, this wave would be in a circle, and this wave would be in a circle. Instead of being this point right here, this would still be at the top of the circle, and this would be at 3 o'clock, or yeah, 3 o'clock. That's what I'm trying to say, about 90 degrees out of phase. So as this one is at its peak, this guy starts. When this guy's at its peak, this guy's finishing. That's all we're really trying to say, is that because of this inductance, the current is going to lead, so voltage is going to lag by 90 degrees.
That is kind of important in the real world when you start looking at dynamic switching in motors, like motion control, speed control for sure. Speed control of a DC motor, which we'll start to talk about. This kind of stuff right here is very, very important for that as far as our world is concerned in a practical sense. So, moving on. Everybody clear on that? Voltage, or current leading voltage by 90 degrees. Okay. All right. So this is my graphic right here. This is theirs. The induced voltage is going to lead in this case, since it is the opposite action of the applied voltage, the induced voltage is going to lead the actual current in this case. Everybody clear with that? Since we're 180 degrees out of phase with our reduced voltage, not our applied voltage, then as this circuit current is continuing to flow, it's actually going to lag the induced voltage because it's coming back the other direction. Why do you think these waves aren't tall? The current voltage is not as high as the current in this situation. In this system, although we wouldn't have a sine wave, it would be the voltage and the current would be the same. What do you suppose it would look like in this system? That wave? Straight line.
go crossing the axis from positive to negative on that one. Okay, so here we go again with plugging in voltages and currents
to figure out power. In a pure resistive circuit, true power, or wattage, is equal to the product of voltage and current. But in a pure inductive circuit, no wattage is produced. So voltage and current are 90 degrees out of phase, so they have different polarities 50% of the time. So when the polarity is the same, power goes to produce a magnetic field. When it opposes, power goes back to the circuit as the field collapses. Yeah, all right. Unpack that stuff for us. See if we got a graphic. This is kind of what I was trying to explain with my drawing up here, is that up here on this guy, point of no current change. Let's see, the greatest rate of current change is between here and here. The voltage is produced when the current does not change. So we're losing the current is obviously changing here, so we're inducing voltage right here because the current is changing, right? Okay? So right here, where it's saying the greatest rate of current change is when we're going from our zero on our axis. Right here, it's going to be changing. So at the point that it stops changing, the maximum point is the point that our induced voltage is going to start. Okay. Current lags applied voltage by 90%. Did we just say the current led voltage by 90%? Voltage and current. The pure induction circuit current lags voltage by 90%. Okay, good. Glad we checked that out. Sure. But we're all on the same page. So reactive power. This is going to be pretty much the exact same thing that you're going to see in power, except for instead of a resistor, we're going to have coil, an inductor. So reactive power is measured in VARs, volts to amps reactive. VARs are computed the same as watts, except substitute inductive values for resistive values. And VARs equals the amount of current times the voltage applied to the inductive part of the circuit. Okay, and if everybody pretty clear? When we're talking reactive power, it's almost the same as resistive power, except for just using the different values. Using inductive reactance instead of actual resistance in this sort of circuit. Okay, I think so. There's not a lot to unpack with that. It's pretty much the same thing as the other stuff. So, computing formulas for computing VARs. Voltage applied to the inductor, EL here, times IL, which is current flow through the inductor. And then, what do we got going on here? Here's how we can figure it out with the resistive load. It's basically Ohm's law in induction. Simple stuff there. Nobody having any trouble with that, right? Cody, you good? All right. The quality of an inductor. Inductors contain internal resistance. So even us right here, right now, if we come over here, we know if we were to take this wire and have about a mile long piece of it, let's say 1,000 feet. 1,000 feet of this wire right here. I know this from experience that if we were to meter this wire at 1,000 feet, it would be about 1 ohm. If we did this and we had 1,000 amps, it would be about 1,000 feet. So inductors contain all internal resistance. Geez, I wouldn't think of anything that doesn't have some sort of resistance. And that voltage would be up there really close to zero. Really close. I don't know what I've heard that's the best conductor. It's cold, but
I don't know if there's been any new materials created since I heard that. But the quality is determined by the ratio of inductive reactance to resistance.
So if we're using this wire
On my meter here to connect an inductor, we're going to have inductive reactance. But the difference over that would be actually what the resistance of that circuit would be too. So
that's what the quality is. So inductors with a quality of, or a Q rating of 10 or greater are called pure inductors. Nothing really to tell you there. Total current limiting effect, resistance, and reactance is called impedance. Who remembers the Pythagorean theorem?
Pythagorean theorem. That one that you taught in high school, you know years again? Yep, heard it. A squared plus B squared equals squared. Hopefully you guys paid attention to geometry, or I guess maybe this is why trigonometry. Maybe.
And I bet you we're going to talk about it. Oh, wait a second. Did I take it out of there? I thought we had the triangle to talk about. Maybe it's in the book that I saw the triangle. Did you see it in the book? Yep, there it is. So I suppose what it's trying to tell us here is that the coil impedance is the combination squared of inductive reactance plus resistance. So on our secret little triangle that it's showing us in the book there, the long part of the triangle is going to be the greatest part. So our impedance is going to be the combination of resistance and reactance. So, man, that old math stuff's been sticking with us for a while, hasn't it? Stinking old math. Okay. That's pretty much all I have to say about inductance in an alternating circuit. Let's go through the review here and just make sure that we're all square on that. Induced voltage is proportional to the rate of change of current and opposite the polarity of the applied voltage. Inductive reactance, counter voltage that limits current, like resistance. Current lags the applied voltage by 90 degrees in a pure inductive circuit. The quality of an inductor, or Q rating, is the ratio of inductive reactance to resistance. Pure inductive circuits consume no watts. Reactive power is measured in bar. Voltage, amp. What does it say? Voltage, amp. Somebody help me. Yeah, thank you. Thank you. Okay, now, when we finished up the other day, I talked to you guys about bringing down some show and tell. We talked about this earlier today when we were talking about voltage spikes in a inductor. And what we have here, because you guys probably didn't get to spend a lot of time with them before, you know what this is. See it before? Diode. Right? This little tiny thing is the exact same thing as this big thing. This is a diode, so we use this quite a bit in light. It almost looks like the symbol on the hat, funny enough. So everybody remember what the symbol of a diode is? You plan that out. Everybody did. Who remembers? Triangle with the lines from it, with the line going through it. Okay. Who knows what this guy is? LED, light emitting diode. Pretty much the same thing, except for byproduct is light. Good stuff. Okay, and what do I got you? 5 more minutes right here. What do we think this is? Little tiny bucket. I should put them on the screen. Anybody? Can you see it?
Oh, transistor.
Close. Relax, I'll tell you. Yes, Bill? capacitor's only got 2 legs. Instead of 3. Close. Trial is close. Nope, not a resistor. This is an SCR. So looking into a rectifier. Sometimes I believe they're very similar to what's called a triac. Very similar. These little guys right here. But this is also an SCR. This is a big line SCR. This allows thousands of pass through. Whereas we put it in there. This guy right here is essentially the same thing. We have the pretty much the same thing as what we got going on right here. It tells us by looking at this that, hey, I bet you that voltage and current flow through direction right here because it looks like it's going through here, and it doesn't really feel like it should go through here because it's got this big thing on the end of it. So that's exactly what it is. Visually, it's like, oh, looks like that current passed through here, but we don't want it to pass through here. So with the diodes going that way, this is almost essentially the same thing, except for we are going to be able to control when this guy fires and when it doesn't fire. When the switch closes inside, will allow the voltage to pass through by using this little guy right here, this little white wire. And I think on this guy, it's typically the middle that we use on this guy, but this is called the gate. And we apply a small voltage to this to be able to start the circuit inside of here to allow this to conduct. This is where we're going to be spending some time, maybe not so much with DC generation, because that's just going to be very simple stuff. But as far as DC motors are concerned, these guys right here are very important because of the actual industrial scale. These are what we're going to use to translate the AC voltage to the DC voltage. So I brought this down for some show and tell, so we can start to have that in our mind as we move into AC to DC conversion and conversion to be able to control our DC motors. So what we got? 2 minutes left.
Any questions? So we're going to have ourselves a little bit of an exam.
Yes, Lena. So, yeah, I have the exam for 135 is already ready for today, as soon as we get here tomorrow morning. Wednesday morning, Tuesday. So we'll get into that class. So please, everybody, look me in the eye. Remember your computers. Who doesn't have them? You don't have a computer? Okay. Bring one. Phil, if you can't get your computer here, I think that Scott said I can send it to the library to take the test. So. Yes. So, no, we're going to do 135 tests in class, and I'll have you guys do the. We're going to do this one for our 133 test in here on Friday for So I've already started making it. It's going to be a little more difficult than your 135 lab. All right, 135 testing, just because of the fact this is a really more difficult concept and no color. Pay attention to the summary. There are going to be questions asked from the review questions. Let's see. I'll see approximately how long it goes, but if I can keep it under 30 questions, I may allow for a little bit of review at the beginning of the class. But the reason why we're moving forward getting some tests done is because I got to have you guys full grades in by the 3rd. I think that's a week from Friday. I have to have grades in. And those of you who don't have a passing grade are most likely going to get that information. So for this class, what we have is your homework assignments for the grade. Suppose you don't have homework assignments in for yesterday and today, you have 0. If there was arrangements made with me today to extend the date, extend the time period on allowing you guys to get those in tonight, then you'll have a 515% reduction. I'm kicking around an idea of maybe making like a 10% reduction, maybe no longer a lot of time to be able to submit that. That kind of defeats my purpose of wanting to review those questions at the beginning of class. And I'll try to iron out a few problems that we have in the moving forward. So we actually get some good job. What's that? Yeah, that's my goal is to have this first unit test, and then, like I said, guys, these review questions are for your benefit. So I'm not even, I look at everyone and I make sure that the answers are matched up, which is great for you guys because that gives you the opportunity to hold on if you don't have them picked out. It's all right the same answer down. But no, those are for your benefit. I'm putting those out there for you to be able to spend time with the book, learning the stuff that's going to be tested. So I'll keep, that'll be the book material will be made, based the test on, and then also some of the stuff that we actually talk about. So I can make sure that sometimes in this beginning part of this unit, this class is a little bit cumbersome because we're talking about theory again. Actually, once we start getting into putting our hands on the wires and stuff like that, some of the stuff that we're learning now will make sense. So that's all I got for you. My lab guys, take a few minutes, but I'd like to get started as soon as we can. So that's all right. I will review.
Let me look, because I think I only had two. Philip, please stay for a minute and chat with me. Give me a minute here to make sure that Tyler's got his stuff where it needs to be. And let me stop